Thanks for the introduction, Phil, and thanks to everyone for attending today's webinar on GOEPEL Electronics' new 3D-AOI system. As you'll see from this webinar, this new system is very innovative and very different from anything else in the industry. The system will be available beginning later this year, and we look forward to rolling it out and getting it out there into the industry. With that, I'll go ahead and move forward here. I am going to not only talk about our 3D-AOI system, but I'm also going to give you a brief introduction into who GOEPEL Electronics is. And I'm also going to talk about our new graphical user interface, Opticon Pilot 6.0. This is a new interface that offers a new capability level, and I think you'll find it quite interesting. And it's being introduced. It was actually developed for our 3D solder paste inspection system, but it's now being migrated to our other AOI platforms, and the 3D-AOI system will also include this graphical user interface. I'm also going to talk on our 2D AOI systems. As you'll find as I move through here, really the combination of 3D AOI and 2D AOI is the ideal. Putting those two capabilities together really rounds out the power of both. Bringing them together makes a very effective system, as you'll see. First, a little bit about GOEPEL Electronics. We are a company that produces primarily board test tools. We also have several other divisions that I'll mention. We also have a very large customer base. Our customers develop and manufacture very high quality products. We work with a very wide range of market segments. These include defense, aerospace, medical, commercial, pretty much the full spectrum of markets in which high quality manufacturing of PCB assemblies are performed. We produce very modern products, which are really targeted at modern electronic board assemblies. Our customers are very sophisticated and in many cases produce products for fields where very high quality is required, and their quality needs to be assured. So we're very accustomed to working with these kind of applications. As I mentioned, we have several business units in addition to the optical and X-ray inspection systems. One of the tool sets to the tool areas that we work with very actively is JTAG boundary scan. We not only support the traditional boundary scan applications of connectivity, but we also develop tools that are very focused on extended boundary scan capabilities, such as embedded test, where we can use boundary scan access to access onboard microprocessors or microcontrollers or FPGAs, and use those onboard components as embedded test capabilities. So this greatly enhances the capability of JTAG boundary scan applications and pushes these technologies into a new realm, and we're the market leader in that capability. So if you're interested in that type of electrical test capability, we'd certainly be happy to talk to you about that as well. In addition, we also have automotive test divisions, as well as a division for industrial vision solutions and functional test. So as you can see, there's a very broad range of experience in GOEPEL Electronics, and we bring that all to bear in our products. GOEPEL Electronics was founded in 1991. The founders of GOEPEL came out of Carl Zeiss. So there's a very deep heritage of electrical and optical experience here. We're headquartered in Jena, Germany, which is the home of Carl Zeiss. So this part of Germany enjoys a very long historical technology heritage, and GOEPEL certainly benefits from that. We have offices around the world. Our U.S. office where I'm at is in Austin, Texas. We also have direct offices in France, the UK, China, and India. And in addition, we have many partners around the world that offer additional products and services that enable us to round out our offerings for our customers. Today's focus is primarily on 3D measurements and 3D-AOI, and with our new system, we target producing 3D measurements without the compromises of many of the previous systems and existing systems. Our new innovative 3D-AOI system is, as I mentioned earlier, very different from anything out there, as you'll see. Existing systems are primarily based on various interpretation methods. These use either multicolored illumination or illuminations with different angles in combination with multi-angled camera systems. Most of these systems rely on various forms of triangulation. They produce structured light patterns or use some kind of laser scanning, and then a triangulation calculation is used to estimate or calculate the actual Z height and topographical nature of a particular circuit board. Our system we are terming as a telecentric multi-spot array. That term will become more clear as we go through this webinar. You'll see where all that, the different aspects of that name come from. And as you'll see, this system is very direct measurement system that alleviates many of the problems in the existing triangulation-based systems. The heart of our 3D-AOI system is a chromatic lens that focuses different light frequencies at different focal lengths. As a result, we are able to project an array of light spots orthogonally down onto the board under test. The light being reflected back from the top of the topographical surfaces on the board under test comes back to this chromatic lens, and the chromatic lens interprets the distance to the particular surface based on the light frequency that is generated by the lens. So the camera ends up receiving a signal from the lens that is chromatically separated based on the Z dimension. This lens and camera system is telecentric, and it is also orthogonal, as I mentioned. As a result, we produce very high quality images, and we also avoid some of the issues that are produced by angular systems. To describe that a little bit more accurately, if you look at this diagram, typical 3D-AOI systems are made up of some sort of structured light source that's projected onto the board from an angle. And that projected light source results in a pattern on the board. One of the most common used patterns is called fringe projection. And this fringe projection, or this pattern that's projected on the board, is observed from a camera orthogonally. As a result, as these patterns on the board move across various components at various heights, and since it's being projected at an angle, there's an apparent bend or deflection in the projected pattern. The camera is able to observe that deflection in the pattern, and through triangulation and various calculations, the height of the particular component producing that aberration can be calculated. One of the problems of this particular approach is the shadowing effects that are produced by the light pattern, the structured light source being projected from an angle. Some of these disadvantages include shadows. Shadows are produced between tall components. Since the pattern is projected from an angle, tall components will produce shadows that can fall across other components and other areas for test on the board. Anywhere a tall component produces a shadow, no measurement is possible because the projected pattern is not present in those shadowed areas. So these shadowed areas are a direct loss of coverage, represent a direct loss of coverage, and can be quite substantial on some boards. High package density can also produce shadowing. Even for relatively small components, if the packaging is very densely packed, there can be shadow effects that eliminate coverage on the board due to shadows on critical areas to be measured. These methods can also be affected quite substantially by reflectivity of surfaces. The reflectivity or absorptive nature of the surface can significantly affect the camera's ability to observe the deflection in the projected pattern. As a result, no measurement values can be, there often are areas of where no measurement values can be produced. For example, on a highly reflective surface, the camera may not be able to distinguish the projected pattern, and as a result, no real calculation, no measurement can be taken there. To give you a little better sense of how our system works in terms of the multi-spot array, the telecentric multi-spot array term comes from the nature of the telecentric lens and the array of white light spots that we project onto the board. So the heart of this system, in addition to the lens and camera arrangement, is the projection of white light spots onto the surface of the board under test. This image that you see before you here is actually a projection of those white light spots onto an angled piece of paper. The piece of paper is angled away from us. And as you can see, you can note a color shift as we move across the surface of the paper. That color shift is directly proportional to the change in the Z dimension that is produced by putting the piece of paper at an angle. So this is a really good illustration of how we produce a color shift throughout the Z dimension, and as a result are able to produce this very direct measurement of the height of the surfaces on the board. This spot array is actually scanned across the board. This is done for two reasons. One is the actual inherent density of the white spots projected are not sufficient to produce the XY resolution that we need. So we actually scan the array of white lights across the board and effectively produce more sample areas by sampling and taking measurements as this array of light spots is being moved across the board. This scanning method also is part of our speed capability. Scanning this array of spots across the board rather than stopping and starting allows us to be very fast. Systems that start and stop the mechanical components as the measurement is progressing across a board have suffer from speed issues relative to the need to allow settling time for the mechanical components. Once a mechanical component is stopped and started, or I should say started and then stopped, once it's stopped, a certain amount of settling time needs to be allowed to allow those mechanics to settle down. By scanning the array across the boards, we alleviate that issue and are able to make a continuous scan and this produces much faster scanning times. The measurement module that is at the heart of the 3D-AOI system is called the 3D-IZ system. You can see an image of this component. It's highly modular, and you can see an image of that component on the right of this slide. Since it is modular, it can be combined with standard 2D-AOI modules. As a result, we can bring the 3D capability together with our very capable 2D systems, producing an enhanced capability that's represented by this combination. So integration into the AOI systems of the Opticon advanced line, for example, is completely possible. The first systems to be produced are going to be based on our advanced line inline AOI system. But down the line, this capability is going to be able to be integrated into our full line of AOI systems. And again, the advantages of the 3D-IZ system include measurement without shadowing effects. So even between tall components, due to the patented projection and camera arrangement, we can see down between even the tallest components. We can see between even the most tightly packed and high-density assemblies, and we're able to produce measurements across the entire board without effect of shadowing. The 3D measurements are independent of component and solder joint surface. This projection of white light will produce a reflection that we can measure regardless of the surface that's being projected upon. And the high measurement speed in this system, which is based on the camera technology and the lens assembly as well as the scanning methodology, is also greatly enhanced by our adoption of the communication standard Coax Express. This communication standard is 25 times faster than GigE, so we gain a great deal of speed in this new system through adoption of the Coax Express. In addition, we have very fast 3D data processing and display. This is based on a graphic board with 960 CUDA cores. So these 960 cores operate in parallel, giving us very fast processing times and very quick display capabilities. To kind of illustrate the measurement characteristics of this system, you can see on the right here a board under measurement, a board under test here being measured. On the left, you can see the 3D rendering of this particular board. And as you can see in this 3D rendering, you can note the color shifts throughout the z-axis. And you can also note the very fine sensitivity within the z-axis. If you note on the surface of the board, there are some solder pads and different artifacts down there that are very small profile, very low profile, but still show up in this measurement. To give you a little more information on the specs, as I mentioned earlier, we call this measuring technology the scanning telecentric multispot array. And again, the projection and measuring direction is orthogonal and telecentric. As I mentioned, it's very fast. Inspection speeds are up to 70 square centimeters per second. This speed rivals even the fastest 2D AOI systems. So the price performance ratio on the system is going to be very attractive. The XY resolution of this new system is selectable between 10 microns and 30 microns. And the Z accuracy, probably the most important spec here, is less than 5 microns. So as you can see, we have a high degree of ability to resolve variation in the height and the Z-axis of components on the board. The field of view size is 44 millimeters by 32 millimeters, and as I mentioned, we scan that across the board surface to be able to measure the entire board. Measurement functions for the 3D capability for solder joints, they include such things as volume, wetting angles, and shorts. For components, we can measure height, coplanarity, position, and of course this is just a small sampling of the measurement functions. The inspection functions for the accompanying standard 2D AOI capability add to these functions for solder joints, the soldering quality and shorts. For components, the position of the component, the polarity of the component, presence or absence, OCR capabilities, color interpretation capabilities. For example, if you need to measure the color bands on a THT resistor, our systems can bring that capability. Others are identification of fiducials, reading of barcodes and 2D codes. So as you can see, when you bring the 3D and standard AOI capabilities together, you end up with a very rounded overall capability. Some of the measuring functions include definition of measurement areas, definition of the profiles to be measured, and of course the measurement of height, angle, volume, coplanarity, as well as position, as I mentioned earlier. To show you a few concrete examples based on real failures, as you can see in this photograph to the bottom right, the far left pin clearly has a problem. And looking at this optical image, we can see fairly clearly that the pin is deflected to the right. But it's not clear whether the pin may also be lifted or have other deflection characteristics. But if you look at the 3D rendering of this particular failure, you can see very clearly that the pin is not only deflected, but you can also see that in fact it is not lifted. As you can see from this color coding on that on the faulty lead, the color coding really is the same as the rest of the pins. So you can very clearly see that the pin is just deflected to the right and in fact is not also lifted. Another good example is represented here in this photograph. A quick look at this photograph may almost look normal. If you look at the leads closely, you begin to see that there is something going on here. The meniscus on the solder joints don't look quite right, and it's pretty clear that there's something wrong here, but it's not clear exactly what. If we take a look at the 3D representation, we see a much more dramatic representation of what's going on here. And in fact, you can see from this rendering that the component is actually inverted. The component has been mounted upside down. In this particular case, the component was glued to the board, but obviously was not effectively soldered because the leads are actually inverted, and there's no way to produce a good solder joint here. To compare that to a properly mounted component, you can see in this 3D rendering that this particular component looks very normal. One other example I can show you here is with this particular component. If you look at the 6th pin from the left, you can see pretty clearly here that this is not a normal solder joint. But it's not completely clear exactly what the problem is from this optical representation. However, if we look at the 3D representation, it very quickly becomes clear that this is a lifted lead. We can see very easily that lead is lifted substantially in comparison to the others. And suddenly the actual nature of this particular failure is made very clear. To move on to a brief discussion of our Opticon Pilot 6.0 graphical user interface, I'm not going to go into a lot of detail here. Obviously, going into detail on the graphical user interface like this can represent a webinar in itself. But I do want to touch on some of the distinguishing capabilities here. As I mentioned, this is a relatively new graphical interface that we are migrating across our AOI lines, and it has some very, very nice capabilities when compared to our traditional graphical user interface. This graphical user interface is being combined with a 3D-AOI system and has a highly graphical nature. Forgive the German that's left in this particular slide. This presentation was interpreted from German, and we have a few artifacts still remaining. But anyways, you can see here, you can see several slices of the Opticon Pilot 6.0. On the left is our Smart Guide system, which is really an easy start system. This user interface allows even an experienced user to easily produce a test program on this system. In the center panel, you can see a representation of the part of the user interface where library assignments are taking place, where fiducials are identified. Those kind of steps within the test program generation are executed. And then finally on the right, you see a representation of our 3D rendering of the board. As the library assignments are made, components from the library are actually assembled into a three-dimensional graphical representation of the board under test. We can see in a little bit more detail here the user interface where library assignments are taking place. You can see on the left the library components. In the center is the board under test, and on the right is a representation of the component assignments and also a representation of what's tested and what's not tested. The 3D visualization of components and device test with this graphical user interface offers better options for visualization and comparison. And the visualization of devices and test functions in the overview image allow a better check of included tests and as a result, a better intuitive sense of coverage. The user interface incorporates a very modern design with selectable color schemes and is highly adaptable to personal preferences. Again, I mentioned briefly the 3D visualization aspect of this user interface. On the left, you can see a library component. In the library, there's a 3D graphical representation of the components. As library assignments take place on the board, those 3D graphical representations of the components are also added to the 3D visualization of the board. And the end result is a complete three-dimensional visualization of the board under test. Even for an inexperienced AOI user, this graphical user interface can be used to quickly produce a basic test program. If we take a typical application where perhaps a new product is coming online and is to be manufactured during the night shift, but there are no test programs available yet for this particular product and no AOI programmers available during the night shift to produce a test program. CAD data and library for most of the components is available to the user in this case. So the CAD data entry is simple to accomplish, and the library is available in the system to be used for library assignments to the board. When using the Easy Start method, the Smart Guide Increased false reject rates or partial manual inspection may be accepted temporarily. A full coverage of the board may not be possible, but at least a basic test program can be produced. The test program has limited validity period, and then can be optimized the next day by an experienced AOI programmer. So the Smart Guide for fast and easy program generation allows a user to test programs without any prior knowledge, or to produce test programs without any prior knowledge through a full touchscreen capability. One precondition, of course, is that the component library and CAD data have to be available. Even for an inexperienced user, the import of the CAD data and the performance of library assignments is easy, but those do have to be available to the user. Some limits, as I mentioned earlier, is no generation of new library components can be created using the Smart Guide, and no debugging is possible. It's really designed for an inexperienced user or for just a quick generation of test programs in situations where resources may be limited. There are some new options here. Components can be inspected manually or not. You can select whether components can be inspected manually or not. And as I mentioned, limited validity of the test program can be established. To take a quick look at the Smart Guide, as you can see, this is a very simple graphical user interface. It begins with import of CAD data, proceeds through definition of fiducials, and then assignment of library components. And then from that point, a test program can be produced. To show you a quick video that illustrates this flow a little bit better, here's a short video of the use of this system. First, CAD data is imported into the system. Once the CAD import is complete, we can go through and define fiducials and import library components and assign those two components on the board. As you can see, the system is going through and assigning components. It's capable of identifying various packaging, various component types, and automatically making these assignments. As you can see in the bottom right, the selected components 3D representation is illustrated. And as the library assignment completes, and as that's going through, as I mentioned, a three-dimensional representation of the board is produced graphically and is then available for the user. I know that's a very quick and rudimentary representation of the interface, but like I say, there are enough details here that it would take a substantial amount of time to go into great detail, but I did want to give you a basic feel of the system and illustrate its basic capabilities, especially in terms of the ability to quickly and easily produce test programs. In today's environment, it's often important to be able to support high mix and low volume environments where many test programs need to be produced quickly, as well as the situation that I just described where an inexperienced user may need to be able to produce a basic test program. And the new Pilot 6.0 and Smart Guide system graphical user interface provide those capabilities. As I mentioned earlier, the 3D-AOI capability is going to be available in our complete Opticon AOI line. Our Opticon AOI systems range from manual offline systems all the way through the most advanced high-speed double-sided inline systems. and the 3D-IZ modular component will be able to be integrated into this full line of AOI systems. As I have mentioned a couple of times throughout the presentation, we consider the ultimate power to be in the combination of 3D-AOI and 2D-AOI. As a result, I did want to also touch on some of the distinguishing capabilities of our 2D-AOI systems. We use camera and lighting configurations that greatly enhance our ability to detect faults and avoid false calls. Some of the challenges that are posed for two-dimensional AOI systems are represented here in these next few slides. Some of those are hidden components and solder joints, different angles of components on the board. Components aren't always mounted at convenient 90-degree angles. As you can see from the image on the lower right, sometimes components are mounted at 45-degree angles or even other in-between angles. So the ability to handle that is very important. And of course, different pad geometries can also pose very significant challenges. One of the ways we offer a lot of power to deal with these capabilities is in our angle view camera systems. This is our Chameleon angle view camera system that is actually a rotating camera base. Rather than utilizing multiple camera systems, multiple fixed cameras on various different angles like most of our competitors, we choose to mount a high-quality camera on a rotating base. This gives us the ability to not only handle angles of 90 degrees, 45 degrees, a limited range of fixed angles, but this rotating camera angle, or this rotating camera system, can actually be rotated in 1-degree increments throughout 360 degrees. So we can easily adapt to even the most challenging angle view situations. As you can see in this particular example, we're seeing pins through very tall components, and we're able to position the camera in such a way that we can produce a view of these important measurement spots. Another challenge that's often encountered with AOI systems is producing angle view in combination with a large field of view. Typical angle view cameras utilize a focal depth that optimizes image quality. But this focal depth, this focal plane, is generally orthogonal to the camera system. As a result, it's at an angle to the board itself. So when we combine the angle of the board under test with the angle of the focal plane and the focal depth, we see a result here that is a very small field of view. In order to enlarge the field of view in a case like this, we would actually have to use a deeper field of focus. And this, of course, would have a significant impact on the image quality, so is in many ways undesirable. The way GOEPEL handles this situation is we start with the optimized focal depth, but through a little bit of optical magic, we actually angle the focal angle to be parallel to the board itself. By doing this, we're able to maintain the same high image quality and focal depth, but increase our field of view significantly through this angling of the actual focal plane itself. We have found at GOEPEL Electronics that illumination systems can be very critical in producing very effective fault detection, as well as avoiding false calls. We employ an LED-based illumination system that is able to produce light frequencies throughout the spectrum from ultraviolet to infrared. As a result, we can bring the full spectrum of lighting capabilities to the test challenge. As you can see from this particular example, we're going through various different lighting frequencies with a fixed board under test. And as you can easily see here, different light frequencies dramatically change the observability characteristics of the board under test. In addition to that, there are other benefits that come from having a wide spectrum of lighting available. For example, ultraviolet illumination is often very effective in making fiducials more visible and making them more easy to detect. Infrared illumination for component detection with low contrast is very effective. In this particular example, you can see a board that has very, very low contrast. We can see leads and solder joints and to some extent traces in this example, but you can't hardly see component packages at all. And it's very hard to really make out the full spectrum of connectivity and measurement opportunities here. However, if we bring infrared illumination to the mix, as you can see here, contrast is greatly enhanced. We can not only see the traces and leads and solder joints much better, but we can also see the packaging and even the markings on the packaging much more effectively. So as you can see, having a wide range of illumination options available can be extremely powerful in optimizing detection and minimizing false calls. So with that, just to kind of summarize what we've gone over here, this is a completely new 3D technology which allows measurement without shadowing effects and completely independent of component and solder joint surfaces. Whether the surfaces are reflective or absorptive, our multi-spot array is able to project and project a lighting, and our camera systems are able to detect reflections from that lighting and interpret the Z dimension depth. We produce very high measurement speed, largely due to our innovative technology in the image capture. And we also offer availability in all of our inline and standalone systems of the Opticon AOI series. So by offering these capabilities, these direct measurement 3D capabilities, the high speed of our high performance processing capabilities, and availability in our full line of AOI systems, this new 3D modular component greatly enhances our AOI offerings. The modular design offers for the highest inspection depth in combination with our 2D modules, including coaxial and multispectral illumination, as I mentioned. So we can bring the full angle view and multispectral illumination capabilities into the same system with the 3D capabilities. Our rotating angle view camera module, Chameleon, is available in combination with the 3D AOI system. And our new Pilot 6.0 and Smart Guide user interface offers effortless, user-friendly, and clearly structured test program generation. Thanks much for your attention today, and I think we have some time now where we can field a few questions. I hope you enjoyed the webinar, and if you think of any additional questions after we're finished here, please feel free to contact us for more information or answer to any of your questions. Thank you very much.